Okay, so let's get into nuclear chemistry. Again, like organic, we're only going to really do the basics. First of all, what nuclear decay is it's how a nucleus can actually change. We've spent all of our time, a year and a half, doing chemistry of electrons and assuming the nucleus is going to stay the same. But when you hear of radioactive decay or words like that, what that is the nucleus decomposing, hence the word nuclear. Nuclear meaning the nucleus is changing. So you have a certain number of protons and neutrons in the nucleus. Well, this is going to change that. Now, there are 4 different ways a nucleus can change. The first is through something called alpha particles. You can see those on your paper. Then there's beta particle decay. There's what we call positron emission, and something called electron capture. We're going to run through all 4 types. Right underneath there you see a little picture of an X-ray. Also in this process, when a nucleus decays, it also gives off energy. Okay, and that energy can be used for things. That's why like a nuclear bomb is so explosive and powerful, is because of the energy that's given off with those. So let's go ahead and start with alpha decay. Now you need to be familiar with each type. You'll see some examples of the types of problems that you'll be doing with them. The first thing you have to understand about alpha particles is that essentially what an alpha particle is 2 protons and 2 neutrons. Okay, so you're going to have a nucleus. I have a picture here. So you're going to have this big nucleus, okay? Most of the time, and you'll learn this in a few minutes, but most of the time this happens with really big nuclei. And it's unstable the way it is. So what it does, you can see this arrow, is it's going to release this right here. This is the alpha particle. It's going to give off an alpha particle, which is 2 protons and 2 neutrons. That alpha particle will go off into the world and do its thing, which we're not going to discuss what its thing is, but it goes off and does its thing, and it leaves behind a smaller, more stable nucleus. Okay, and we'll talk about why that happens and how we know that type is going to happen, but just for now, understand that if we use the term alpha decay, we're saying the nucleus is giving off 2 protons and 2 neutrons. Now there's 2 symbols. We write these equations that are called nuclear equations. There's 2 symbols for an alpha particle. The first one is like an alpha symbol, a Greek alpha symbol. Looks like a little fishy to me. And you put a 4 and a 2. The reason you put a 4 and a 2 is that this right here represents the number of protons, just like if you're writing a full atomic symbol. And this right here represents the number of protons and neutrons. So we said we're giving off 4 protons and neutrons total, 2 protons, 2 neutrons, but 4 total. The other thing we could use for a symbol has a 4 and a 2, and it says He. Well, we know He is helium. If you look at the periodic table, you'll see that helium has 2 protons and 2 neutrons for a total mass of 4. So essentially what an alpha decay is a big, huge nucleus spitting out helium nucleuses, okay, and decreasing its mass by spitting out helium nucleuses. Now again, because you're getting rid of protons and neutrons, you're actually getting rid of mass. Okay, this actually sheds a decent amount of mass. So let's take a look at a possible type of equation that you could have for this. So they might tell you that you have uranium, what do I have, 238, which has 92 protons, like so. If they tell you this undergoes alpha decay, this is what you do. You draw an arrow, you say, okay, well, it's undergoing alpha decay, so I know it's going to give off 2 protons and 2 neutrons. If this thing loses 2 protons, it's going to go from an atomic number of 92 down to atomic number of 90. If it loses 4 protons and neutrons, the 238 is going to go to 234, like so. And then I look at the periodic table, and I see what the symbol is for the element that has 90 protons, and I see that that is TH. So this is the nuclear equation showing uranium-238 losing an alpha particle and becoming a completely new substance. And that's what radioactive decay does. It actually changes your element from one thing into something else, because remember, the number of protons in a nucleus dictates that. So that is alpha decay. For beta decay, let's see, I don't have a picture of beta decay, but beta decay is kind of a little mind-blowing, so hold on to your seats for this one. Essentially, what beta decay is one of the neutrons from your nucleus. You know a neutron is neutrally charged. What will happen is that neutron will split itself into a proton and an electron. Okay, I know that sounds crazy, but that's essentially what a neutron is. It's a proton fused with an electron. Okay, that's why a neutron is neutral. So what can end up happening is those two could come apart. If the nucleus is unstable enough, those two could come apart. So it will take a neutron that's in your nucleus and turn it into a proton. The electron is going to leave. The electron does not want to be in that nucleus, and so the electron is going to leave. And that electron is what we refer to as the beta particle. Okay, the electron is a beta particle. So an alpha particle is 2 protons and 2 neutrons. A beta particle is an electron. And you can see on your paper we have 2 symbols that we use for a beta particle, either a beta or we just use an E for electron. And then the numbers that go with this one are 0 on top because there's no protons or neutrons, and then -1 on bottom indicating that it's an electron. Okay, and so again, this is kind of weird. I know this is not normal for you, that a neutron would all of a sudden turn into a proton and electron, but this is what you need to learn is the process for beta decay, and then you'll be able to do these problems. The example that I have in your notes is carbon 14. Okay, so carbon has 6 protons and 14 total protons and neutrons. If it takes one of its neutrons and turns it into a proton, okay, so we're giving off a beta particle, say the problem tells you you're undergoing beta decay. We give off a beta particle. What's going to be left over is this number here. We gained a proton because our neutron became a proton. So now we're going to have an atomic number of 6. We lost a neutron but gained a proton. So this number doesn't change. Okay, that number doesn't change. So the mass, the overall mass, didn't get affected, which makes sense because we lost an electron, and electrons don't have mass. So then we'll put nitrogen there because that is the element that has 7 protons. That's how I picked nitrogen. So that's the nuclear equation for that one. Okay, so that is beta decay. And again, if any of this seems fast, you can go back home tonight too and watch this again. Now, that one was crazy. If you found that one crazy, that a neutron could become a proton and an electron, then hold on to your shorts because this one's going to get even weirder. The next one, if you go to the next page, is called positron emission. Okay, positron emission. This is what positron emission is. We take a proton. Okay, proton is a massed particle with charge, and that massed particle gets stripped of its positive charge, which leaves behind a neutron. Now, obviously, there is more to it than I am saying, but we do not have the time to get into it. So I need you just to accept and sort of get this picture in your head. And then when you go off to college in your 4th year and you are doing nuclear chemistry, you can understand this whole process better. But really, you have a proton becoming a neutron. So it's being stripped of its positive charge. So what the other resulting thing, what will be left off, is this thing called a positron. Now, a positron is like an electron, but with a positive charge instead of a negative. So essentially, it is a massless positive charge. So essentially, you're taking a proton and you're stripping it of its positive charge. And the symbol for it is like the electron, where it will be a beta, but it'll be a 0 and a +1 to indicate that it has a positive charge. So if we did the example, say we have carbon 11, and it tells you to undergo positron emission. So your product is going to be a positron. Now, if we took a proton, we had a proton, and we turned it into a neutron, this proton number is going to go down to 5. We lost a proton. We lost a proton but gained a neutron, so this number doesn't change. Again, this was a massless particle, so the mass, overall mass doesn't change. And then we look at the periodic table and we see that the element with 5 protons is not nitrogen. Sure, you're all laughing at me. It's boron. Okay, so that's the element this turned into, was boron. Okay, so depending on what process is happening, your nucleus is going to change into something else. I'll explain in just a second how we know which one to do. Okay, but we definitely need to be able to understand all the different types. Now, there's one more type. Here's positron emission, it looks like. So you see a proton becoming a neutron and becoming a positively charged electron. Okay, so it's breaking up into those 2 pieces. Now, this is electron capture. Electron capture, we're going to take a proton and it's going to capture an electron. So an electron's floating around outside the nucleus. If it gets too close to the nucleus and the nucleus is unstable, the nucleus can actually swallow it up. It can grab it and fuse it with a proton. And if you remember from what we said with beta decay, a neutron is really just a proton and electron fused together. So if we fuse these two together, voila, we now have a neutron. Okay, so if we looked at the example that you have in your notes for this one, you'll notice that it's the same example that we just did for positron emission, because these two processes yield the same result. So if I have carbon-11 and it can find an electron floating around too close to its nucleus, so I put this on the reactant side, it finds that electron, it pulls it in. It's going to take one of these protons and turn it into a neutron. So I'm going to end up with 5 protons. Mass is going to stay the same because a proton became a neutron, their same mass. And then the element with atomic number of 5 is boron. Okay, so it's the same result for positron and electron capture. So draw a little bracket between your positron emission and electron capture, and just write yourself a note that they yield the same products. They end up with the same result, so you can use either one for that. Okay. Now, how do we know what process to be using? Okay, how do we know whether or not we're going to undergo alpha or beta or positron or electron capture? It's actually quite straightforward. You're going to undergo alpha decay. Okay, so the alpha decay is for atoms, and you can see this if you go to your notes, it says to determine. Okay, alpha decay is going to happen with anything that has an atomic number of 84 or higher. Okay, and the reason for that is that 83, bismuth, is the last stable nucleus on the periodic table. From 84 and higher, those nuclei are just too big. They're too big, too many protons and neutrons. There's just no way for them to be stable. So they have to get rid of some of their protons and neutrons to be able to get stable. So anything bigger than number 84 or bigger is going to be alpha decay. Okay, you're going to know for sure that that's what type of decay it's going to be. Now, if it's lighter than 84, so 83 or lower, then the way you decide is this. You have to look at the isotope that you are specifically looking at. So I have 2 examples down on your paper of carbon-14 and carbon-10. Okay. If you look on the periodic table, the average atomic mass for carbon is 12. Okay. If your mass of the isotope that you are looking at is greater than the average, as it is with this first one here, then, and you can see this on 3A, if it's greater than the average mass, then you're going to undergo beta decay. All right, it's going to undergo beta decay, which means it's going to get rid of a neutron and make a proton. Okay, if it's greater than the average. If it's less than the average, then it's going to undergo either positron emission or electron capture, and you can use either one. They are interchangeable. The AP test would never put 2 options on a test that were the exact same for positron or electron capture, because they both are possible and they both will yield the right result. If you notice the products that form for both of these, one of them makes nitrogen 14, the other one makes boron 10. Atoms' nuclei will be most stable when there's an equivalent number of protons and neutrons. So the closer you get to an even number of protons and neutrons, the more stable it's going to be. So if you ever forget which one of these to do, that will often help you with determining that. Okay. Now the last thing that's on the paper says half-life of radioactive decay. We're going to hold off on that one. I'm going to explain that one to you guys in class. I just want you working with the types of decay. So go ahead to the back side of your packet, and you are going to work on those questions. You are not going to do number 6 at this point, and you are not going to do number 10. And you are not going to do number 12. So skip 6, 10, and 12. The other ones you can go ahead and start to work on, start to talk about, start to think about. If you are done with the notes, you can head back into the lab station with a small group at a lab station so you can talk about them and work on it. Okay? And I am around to help. Oh, look, manometer problems. Exciting.